Hello, good morning.
Good morning, sir.
Morning. So yesterday we understood one sample program on the part B, how to blink an LED or how to control the blinking of LED. So we tried executing it in multiple forms. So we simulated it on the Keel IDE and we also simulated it on the Protest simulator. So I guess you have understood how the part B programs are going to work. And then day before yesterday, we had started our discussion on the core of the embedded system. And so this is what we understood. These are all few things that we're going to discuss in this chapter, core of an embedded system. Okay. We went through the core components of the embedded system: memory, sensors and actuators, communication interfaces, both on-chip communication interfaces and also the external communication interfaces. Okay. And in external, again, two types of communication modules: wireless communication modules, which are in the form of Bluetooth, Zigbee, Wi-Fi, Edge, GPRS, all these things, and then wired communication modules like RS-232C, RS-485, all these things, and then embedded firmware, and we went through the other components of the embedded system. So we haven't discussed them in detail. It is only the brief thing that we understood. And then the learning objectives we understood. And then we understood the different type of memories that we are going to discuss here. So both read-only memories and random access memories. Then the how to interface various external devices like LED 7-segment display, buzzer, which is a device which emits an audible sound, stepper motor, relays, matrix keyboard, or short form you can also call them as keypads, push button, uh, all these things, how to interface all these things with the microcontroller. So when you're interfacing with the microcontroller, you don't require an additional interfacing device. And that is what we understood in the previous class yesterday. We connected directly the LED to the port pin of the LPC2148. But if you want to connect, say, an LED to the microprocessor, so it is not possible directly. So you got to make use of 8255, which is a programmable peripheral interface device. So since we are discussing only on the microcontroller, that is LPC2148, so we are not going to discuss much detail on 8255, but at the end we discuss it. Okay, only on the lighter part we discuss this 8255 also, which is a programmable peripheral interface device which is used for um, connecting the external devices with the microprocessor. But 8255 is not necessary for LPC2148, so microcontroller. So it has the ports already inbuilt in it. So using those ports, you can go for connecting all these things. But when you're connecting some high-end external devices like the stepper motor or the DC motor or the matrix keyboard and all, okay, LED 7-segment display and LED LCD display, all these things, even LCD also not possible. For them you require separate driver ICs. So but those we call them as the driver ICs, but they are not the interfacing ICs. Okay, so usually the stepper motor and all, they require very high voltage, so for them to operate. But the maximum voltage that you can take out from the LPC2148 is ports of the LPC2148 is plus 5 volt. So if the stepper motors comes in plus 12 volt, plus 15 volt, okay, and plus 24 volt, now your LPC2148 ports cannot supply the required voltage for the stepper motor. So that time what we do, so from the ports of LPC2148, which we are getting plus 5 volt. We give it to some other IC, okay, so driver IC, and that is going to amplify the voltage and drive the stepper motor. Okay, so only for that purpose we make use of the driver ICs. Okay. Then we learn about so these are the things, communication interfaces. So I think we have done all these things. Let me skip. Now from here we got to discuss. Yes or no? Is it from here we need to discuss? Hello? Please unmute and talk. So I can't hear you people. So one of you please unmute. Can you hear me?
Yes, sir.
Okay. So from here, right, we need to discuss for today. So all those things was covered in the previous class. Okay. Now, so we'll understand. So can you people recall this slide? Was it done? No, right?
No, sir. No, sir.
Now, the typical embedded system. So embedded system contains a single chip controller. So why we call it as a single chip controller? Because it is system on chip. So we have microcontroller, ROM, RAM, everything present on the same chip. Hence, we call it as a single chip controller, so which acts as the master brain of the system. And the controller, the single chip controller, can be a microprocessor, or it can be a microcontroller, or it can be a microcontroller, or even it can be a FPGA also, field programmable gate array device, or sometimes DSP, digital signal processor, sometimes the application specific integrated circuit. So you can also call it as application specific standard product, ASSP or ASIC. Later we are going to discuss on all these things. So the single chip controller can be any one of these things. Either it could be the microprocessor, microcontroller, FPGA, or DSP and ASCI, application specific integrated circuits. The ICs which are manufactured for a particular application. So those things we call them as application specific integrated circuits. And what all these things, why are they called as master brain of the system or master brain of the embedded system? Because so they regulate the physical variable and also manipulate the state of some devices by sending the control signals. So these things are called as master brain of the embedded system because they can do this. What they can do? So they have the capability of regulating the physical variable and also manipulate the state of that variable and send the control signals to the actuators. So activators are connected to the output ports of the embedded system, whereas sensors are connected to the input ports of the embedded systems. So using the sensors, the embedded system gets the data, takes the input, performs the processing, and then manipulates the state of the variable and then sends the changed variables to the actuators, and the actuators are going to function accordingly. Okay. So if I say an embedded system is designed for the purpose of controlling, then it should have one or more actuators connected to the output ports. It should be connected to one or more output ports of the actuators. Next, so this is a simple example where you can understand. See, we have here this can also be what the sense organs. Okay, so eyes, ears. Okay, so nose also. So it is missing. So and similarly this and what we speak is actuator. So based on the brain signals that are generated, okay, so you can go for making the appropriate actions. And similarly, if I take the computer hardware, Now using all these devices, I can give input to my kernel. So program, my application program is running here. When I give the input, it goes to the kernel, and my application program uses those inputs, processes the computation, and then again produces the output. So the output again is displayed using any one of this unit. So if the information, okay, if you want to present it to the user, so then you can go for using this display panel, small display panel, or else the information can be presented to the user through the speakers, or even it could be through the gaming pads. Okay. So this is a simple analogy which is comparing the embedded system with the human brain. Next. So keyboards, so input devices I said. So embedded system takes the input from various devices. So either it can be from a keyboard, or short form we can call this as keypad. So it can be a push button switch also. So it takes input from all these things, okay, and produces the output. Okay. Now all these things, LED, liquid crystal displays, electric buzzers, etc., so are connected as output devices to a typical embedded system. Now, if I take the example of a mobile handset application, so you can see for taking the input from the user, so we have a keypad or a keyboard. So user interfaces like a keyboard for taking the input from the user, and a display unit, a small display unit for providing the users the status of various activities in the progress, or to present the user with the information. So the mobile handset uses a small display unit or small display panel. Now elements of the embedded system. So this is the core, system core, and this can be a microprocessor, microcontroller, DSP, and then application specific integrated circuit. So it can be any one of those things. Okay. So this is what is the core, and it is written over here. It can be an FPGA. So FPGA, the advantages are out there. Plenty of advantages of using FPGA. So using FPGA, it is also possible for you to reprogram the firmware in FPGA. But all other things, it is not possible. So the system core can be an application specific integrated circuits, digital signal processor, or it could be the system on chip, microprocessor or microcontroller. Now, as you can see, so this system core is attached with a memory. So what kind of memory this? So this can be various types of ROMs we understood. So one-time programmable ROM, okay, electrically erasable programmable ROM, and UV RAM. So ultraviolet erasable read-only memory. All these things. It can be any one of such memory which is holding the firmware, or sometimes it can also be a flash memory. And then the communication interfaces. Say if I want to make my system core communicate with the external world, so then I go for using the communication interfaces. So either a serial communication interface or a parallel communication interface. And again, this communication interfaces can be wired communication interfaces or wireless communication interfaces. And we have communication interfaces within this chip also for making all these components to communicate. So memory to communicate with the system core, and then the sensors to communicate with this. For everything, there is an internal communication link or a communication interface. And next we have the input ports, so also to which we have the sensors connected, output ports to which the actuators are connected. Okay. So, and other supporting integrated circuits and subsystems can also be connected with the system code. And this diagram is basically depicting the major elements of the embedded system. Next. Now, so system code is here. Now, what are the possible system codes? And this is the one which is called as the master brain of the embedded system. Okay, master brain controller of the embedded system, and it can be any one of all these things. So it can be a microprocessor, so which is in the form of 8085 or 8086. Okay, so and then microcontroller. So this 8086 is a 16-bit processor. Your seniors used to study this 8086 earlier. So now instead of you studying this 8086, which is a 16-bit microprocessor, sorry, it is not a microcontroller, it is a microprocessor. So instead of studying the 16-bit microprocessor, so you people are studying the ARM microcontroller, that is LPC2148, which is based on the ARM7 design. Then we have microcontroller, so it can be from many companies. So microcontrollers are there from Atmel. So microcontrollers are there from Atmega. See, Atmega microcontrollers are the one which are most widely used in what is that? Arduino UNO boards. So Atmega 16 is most widely used in the Arduino EN1 boards, and then so ARM, what we are understanding. So ARM I is nothing but because ARM comes with many versions, and the version that we are discussing is ARM7. So ARM 1, ARM 2, ARM 3, ARM 4, ARM 5, but the version that we are discussing here is ARM7. Okay, so this is when I say master brain controller, it can be a microcontroller also, and a microcontroller can be one among these things. Apart from that, it can also be a field programmable gate arrays. Now, why they called as field programmable gate arrays? Because you can go for completely reconfiguring the functions of a software. So it is possible for you to completely redefine the functions of the software. And that is what is the greatest advantage of using field programmable gate arrays in the embedded system. Okay. Is a chip that is completely programmable and can be reprogrammed. So if I use a microcontroller, okay, within the embedded system, or a microprocessor within the embedded system, then it is not possible for you to reprogram. So the software is a firmware which is permanently stored inside the ROM. It is one-time programmable, and after that it is not possible for you to make any changes. But FPGA is used, it is possible for you to reprogram it anytime. Next, ASCI, that is application specific integrated circuits, and one such example is mentioned here, ADE 7760. So this is the application specific integrated circuit which is used in your energy meters, so power meters. I don't know if you have seen at your home. Okay, so all of you will be having a single phase energy metering board. So using that metering reading, so electricity bill will be provided. So inside that single phase energy metering, okay, so there is an application specific integrated circuit which is called as ADE 7760. So ADE 7760 is the application specific integrated circuit which is found inside a single phase energy metering, okay, device. And then firmware, okay, embedded firmware, if you take, it is basically designed to regulate the physical variable connected to the input port. Okay, so say I have the microcontroller, the microprocessor, but if there is no firmware which is present inside the ROM, so then the microprocessor doesn't know how to regulate the physical variables that are connected to the input port. So through the firmware software, you got to tell the microprocessor or the microcontroller how it should go for regulating the variables connected to the input port. Not only regulating, also for manipulating the state of the variables and sending the appropriate output to the actuators. Now, all these things is governed or controlled by the firmware software which is there inside the ROM. Okay. Examples for the input devices, this we have already discussed. So for embedded system, you can have a keypad, push button switches, and various sensors. Now, what is a push button switch? So push button switches are normally different from the other type of switches. So if you push the push button switch, and if you release your finger, it comes to the original state. So those types of buttons are called as push button switches. So when you are pressing the push button switch, which is connected to a port pin of the uh, port 0 or port 1, what will happen? An external interrupt is generated and it is sent to that particular port pin. Okay. And then you can go for writing your own piece of code, what your microcontroller should do when it receives the interrupt or external interrupt through a port pin. Okay. So we have an example on that. Okay, one lab program on external interrupt. So we'll try to understand that. And again, we are going to make use of the push button itself there also. So push button is used in order to generate the external interrupt. Examples for the output devices. So these are some of the examples for the output devices. So we have LED light emitting diode, so which we have already used in the previous class. So liquid crystal displays, so buzzers, so motors, again two motors we understand here, stepper motor and DC motor, and then cathode ray oscilloscopes, CROs, etc. So these are all some of the examples for the output devices that could be used in the embedded systems. Next is memory. So why memory is necessary? Because without this, it is not possible for you to hold the controlling algorithm. So the controlling algorithm for performing the computation. So memory is very much essential. So for holding the controlling algorithm. What is this controlling algorithm? Controlling algorithm is nothing but your firmware. So the firmware software which is stored inside the ROM is called as the controlling algorithm. And why it is called as controlling algorithm? Because this is the one which is responsible for regulating the state of the input variables, and also for manipulating the state of the input variables and produce the new output variables. So hence we call it as a controlling algorithm. And then ROM is widely used for storing the controlling algorithm in ES. In embedded system, read-only memory. This is what is most widely used. And we have other type of common memories also for holding the controlling algorithm. So some of the examples are, you can say these are all the different types of ROM also. So one, we have OTP, that is one-time programmable memory. So that means this memory is programmed only during the manufacturing. So it gets programmed at the time of manufacturing, and after that it is not possible for you to change. And then we have PROM, so programmable read-only memory. So then firmware is used, stored inside the ROM, so but it can be programmable. So how? So sometimes it is programmable by using the ultraviolet rays. So you can expose the ROM to the UV rays. So and you can erase it, and you can go for writing the new program. It is also possible for you to erase the content of the read-only memory by using electrical signals. Okay, and another type of memory is the fast memory. Okay, sorry, flash memory. So these are the different types of memories which we can go for using in order to hold the controlling algorithm. So understood till here?
Yes, sir.
Okay. Next, core of the embedded system falls into any one of these categories. So first thing is general purpose or domain specific processor. So this DSP is a domain specific processor, and microprocessor is general purpose, and microcontroller is for the specific purpose. Okay, so you can go for using all these things. So what you are seeing here is a general purpose microprocessor, that is Intel Core i7 processor, and this is a domain specific processor which is mainly used for what processing the multimedia data, so audio data, video data, all these things. Okay, to process that we go for using the DSPs, because these are the uh, devices which are specially prepared and manufactured for processing the audio and video data. Okay, it is much faster. So you cannot compare DSP processing the audio video data with the normal general microprocessor processing the audio video data. So since these are specialized for processing the multimedia data, so they will process it much faster than compared to the other general purpose processors. And this is what is the Arduino UNO board which you're seeing, and this is the microcontroller. And then sometimes, most of the time, the microcontrollers which are used within the Arduino UNO boards are the Atmega 16 microcontrollers. The next, apart from these general purpose and domain specific processors, so you can also have application specific integrated circuits. I gave one example for this. So that is an integrated circuit ADE 7760, which is used in single phase electricity metering board. Okay, and then programmable logic devices, PLDs. Again, why they're called as programmable logic devices? It is possible for you to reprogram these things. Then commercially of the shelf cards. Okay, these are again the components which are available in the open market. So if you would like to use, you go buy and you can use inside your system. Okay. Next, so merits, drawbacks, and application areas of microcontroller and microprocessors. So what we have already understood the detailed differences between the microprocessors and microcontroller. So, but our focus here is on understanding the merits and drawbacks, advantages and disadvantages of microprocessors and microcontrollers, and discussing the various application areas of both microcontrollers and microprocessors. Now, first coming here, the microcontroller. So one disadvantage that I can say is, so they're designed to perform only a specific task. So they can do only a specific task. That is what is a major drawback I can say. So they cannot perform wide range of tasks. And then microprocessor, if I take, so they can perform unspecific task. So any task, like, so starting from the, even using microprocessor, you can go for developing a software. So you can build games, websites, photo editing tools, creating documents, etc., and plenty of things you can do. Okay. But microcontroller needs to be done, and the output is defined. So this is what. So microcontroller, they do only specific task. Hence we say the output of microcontroller is always deterministic. But the output of microprocessors is non-deterministic. So because they're non-deterministic, because within the microprocessor, input and output for the microprocessor is not defined. Since they are the general purpose computing system, so you cannot define always this is the input and this is the output and this is what is expected. So that is only possible in case of microcontrollers, since they are designed to perform a specific task. So next is now what kind of resources the microprocessors and microcontroller uses. Since microcontrollers are designed to perform a very specific task, so they need small resources, very small resources they need. Small resources like very small RAM, small ROM, and even the limited IO ports are required. And hence, no, it can be embedded on a single chip. And that is what the specific way, since they are designed to perform the execution of very specific task, so it makes this system on chip. So because all resources are smaller in size and everything can be integrated on a same single chip. So for that purpose we call, so majority of the embedded systems are system on chip. You have the entire system on one single chip. But microprocessors, they need high amount of resources. Very high amount of resources is required, like huge RAM is required, external ROM is required, and I/O ports are required. So this is another distinguishing characteristics between the microcontrollers and microprocessors. So microcontrollers can be made a system on chip, and microprocessors it is not possible since they need large amount of all these resources. Another difference between the microprocessor and microcontroller is with respect to the clock speed. See, microprocessor clock speed, microprocessors operate at very high clock speed. So these days we say we have the microprocessor with 2 gigahertz speed or 3 gigahertz speed or 4 gigahertz speed. But microcontrollers, so their operating frequency is in terms of megahertz. So and that too normally majority of the microcontrollers they go for using 30 to 50 megahertz frequency as their operating frequency. Okay, so and the microprocessor, so they operate at very high clock frequency, and this 1 gigahertz whatever written is very less. So these days we have the microprocessors operating at 4 gigahertz speed also. So even our phones are operating these days with 1 gigahertz and 2 gigahertz speed. So and another thing is microprocessors cannot be used standalone. So they need other peripherals. Okay. So since we don't call microprocessor as a system on chip, so it needs other peripherals like RAM, ROM, buffers, okay, I/O ports, etc. And all these things has to be designed and kept around the microprocessor. And this is making the microprocessors very costly, okay, because so along with the microprocessor, we got to invest on the RAM, ROM, buffer, and I/O ports and all. So application areas of the microcontroller. Where are the microcontrollers used? So microcontrollers are used in mobile phones. So this we have understood from the long back. Okay. So all mobile phones are based on the ARM Cortex. Okay, microcontrollers. So we have them in CD and DVD players. So we have them inside the washing machines. So we have them inside the cameras. We have them inside the security alarms. We have them inside the microwave ovens. Plenty. So the list will not stop here. So there are plenty of application areas of the microcontroller, and even we have understood in detail in the earlier classes. Okay. Application domain of the embedded system, we understood around 11 application domains. And then application areas of the microprocessor, so calculators. So sometimes we have the calculators built using the microcontrollers also. So accounting system, gaming machines, complex industrial system, data acquisition system, military applications, communication systems, your personal computers and laptops. So plenty of examples you can give even here also. So now looking at the major differences between the microprocessor and microcontroller. See the very first difference, the architecture. So architecture of microprocessor. See how it is looking, and the microcontroller. So see everything is connected. So we have the read-only memory, and then what is it? RAM, serial interfaces, I/O ports, timer, everything. So seamlessly connected. What does it mean? All these components are there on a single chip. Okay. And if you look at the microprocessor, see, it is only a processor, it is only a microprocessor, and it doesn't have all these things built inside it. And all these things are external components and which are connected to this microprocessor by using a system bus. Okay. So many such buses will be there. So by looking at this architecture, you can know so why this microcontrollers are called system on chip and why this microprocessors are called as independent. And everything needs to be connected by using a bus system or the bus architecture. Okay. So let us start understanding each one of the differences in detail. So microprocessor is the art of the computer system or the laptop systems. So now microcontroller is the art of an embedded system, or you can say master brain of the embedded system. Now here, so it is just a microprocessor. It is just a processor. It doesn't have any other things. So memory, all your components, they got to be connected externally. So that is what is done over here. Everything is external and all of these things are connected to the microprocessor by using the external bus system. So now if I come to this microcontroller as external processor along with the internal memory and IO components. So microcontroller as a processor. So this is nothing but a processor with all these things internal memory and IO components. So since memory and IO has to be connected externally, the circuit becomes large. So the systems which are based on the microprocessor, it is not possible you to make it small because all these things need to be connected externally. And obviously the size of the system becomes heavy. But here, since the memory and all IO are present internally, the circuit is very small. So that's the reason we say system on chip. Everything is there on one single chip, or everything is accommodated on a single chip. So cannot be used in compact systems and hence inefficient. Since everything is external here and the size of the system becomes large, so it is not generally recommended or preferred to use microprocessor. So in the very compact systems that you are building, then what is recommended for use in the compact systems? So the recommended is the microcontroller. If I say I want my system to be very small and do only a specific kind of task, then you need not use a microprocessor, then you can go for using a microcontroller. Microcontrollers are widely used in the compact systems or very small systems. So now if you take microprocessor, the cost of the entire system is high or more. Why? Because so all other components are external. Okay, so we don't have all these things coming along with the microprocessor. So the cost of the entire system is high. Now here, microcontroller, the cost of the entire system is low. Why? Because we have everything on a single chip. You're spending only on a single chip. And if you buy that say chip, so you have read-only memory inside that, random access memory is there, serial interfaces are there, IO ports are there, everything is there. Okay, next. So due to external components, since all these components are connected externally by using a bus architecture, the entire power consumption is also high. The power consumption by the microprocessors is high, and hence it is not suitable for the devices running on the stored power like batteries. That means it is not recommended to use the microprocessor in the handheld devices which are battery operated. But microcontrollers, they are small in size, so and that is the reason they are used inside the compact systems, and they go for reducing the powers, and hence they are recommended for use on the systems which are battery driven. So most of the microprocessor do not have the power saving features. So normally we have, say for example, the laptops or the desktops. So power saving features are also here. So you can go for if you just go to control panel. So power options is there. So there you can go and you can set the idle time. Okay, say after 10 minutes of idle time, I want my display to go off, or after 10 minutes or 15 minutes of time, inactive time, the processor, I want the processor to enter into the sleep state. Now, why we do all these things? Just to go for saving the power. Okay, so we are not saying all. Okay, so most processors do not have the power saving features, but even though it is there, we are not going to use it. Okay, so but here, so everything is implicit. So the power saving mode is implicit to an embedded microcontroller. Why it is implicit? Because the power is very important here, because all the devices are battery operated. So what happens here? So whether you set the option or not, so when the system is in the idle state, so it enters by default into the power saving mode. Okay. By default it enters. Now here it enters into the power saving mode only when you have explicitly set it. But here it is implicit. So whether you set it or not set it, so then automatically after some amount of inactive time, it gets into the power saving mode. Since memory IO components are all external, each instruction will need external operation, and hence it is relatively slower. Say we have a separate memory here. If processor wants to get the data, then the communication should happen through the bus. The data gets exchanged over the bus. Now what is happening? So this way, they're relatively slower. So for that purpose, so the microprocessors are generally designed to operate at much higher clock rate or the clock frequency. But since everything is on the same chip, so microcontrollers accessing the data from the memory or the RAM is much faster, and we don't require, um, yeah, they are much faster. Okay, because all the components are there on the same chip. And then the other difference, if you look at, microprocessors have less number of registers. So we don't have plenty of the registers in the microprocessor, within the microprocessor. We have limited registers. Since there are limited registers and very few registers, and majority of the operations are performed within the memory, and more operations are memory based. So I want to add two numbers. In the microcontroller, especially the microcontroller which is based on the ARM7 design, what we do, we take the data from the memory, we place it inside the register, and then we go for performing the operation. But in the microprocessor based systems, so since we have very small number of registers or fewer number of registers available, majority of the time the operations are performed directly inside the memory. But it is not recommended to do the operations directly inside the memory, and also it consumes a lot of time, because registers are much faster than compared to the memories. Accessing registers is much faster than compared to accessing the memory. So microcontrollers have more number of registers. Why more number of registers? So with the intention of reducing the number of memory operations, so here inside the microcontroller, a large register set is given. So, and the programs can easily and fastly read and write from these registers. Next, so microprocessors are based on the Von Neumann architecture. Now, why we say they are based on the Von Neumann architecture? Because they use a common memory, okay, for or unified memory for holding both data and instruction. Both data and instructions are present inside a single memory. Okay, both. So whereas the microcontrollers, they are based on the Harvard architecture. Now what Harvard architecture says is it uses a separate memory for data and instruction, separate instruction memory and separate data memory, and separate paths also. We have a separate instruction path and we have a separate data path. And with this, the microprocessor can go for accessing both data and memory in one clock cycle. Simultaneously, it can go for accessing both data in memory. But that is not possible in case of the systems which are based on the microprocessor, because it uses a common memory for storing both program and data. So where are these microprocessors are used? So all of you know where they are used. They are used inside the personal computers. And where are these microcontrollers used? So they're used inside variety of devices, starting from the washing machines, MP3 players, lot of examples you can give. So if you start listing, so the list goes never ending. So understood till here? Any doubts?
No, sir.
Okay. So next is digital signal processors. So these are the special type of processors which are designed for processing the multimedia data like audio, video, okay, all these things, and images also. So these are the special type of processor, and again the DSP processors can be of 8-bit, 16-bit or 32-bit, and they're mainly used for multimedia application, for processing and executing the multimedia applications. And since they are specially designed for processing these things, so this DSPs are 2 to 3 times much faster than the normal general purpose microprocessor in signal processing application. Say I'm using the normal, so is it not possible for me to do the execution of a multimedia application using the normal processor? Yes, I can do it. So if I do the same thing using a DSP, which is specially designed for the purpose of processing the multimedia applications, so it will be 2 to 3 times faster than the same application that is being executed by the microprocessor. Okay. So let us stop here. Um, yeah, and so different types of uh, key components that are present inside the DSP. These are all some of the key components. So we have a program memory, data memory, separate memory for holding the program, separate memory for holding the data. So when I say the data here, the data is either the images or the audio files or the video files. And then there is a computational engine which is going to perform the signal processing or the mathematical processing for processing the multimedia data, audio, video, and images. And then I/O units are also there. Input units for capturing the multimedia data, and output unit for displaying the processed multimedia data. Okay, so no worries. We'll continue from here again in the next class. Okay. So from the digital signal processors in the tomorrow's class. So if you have any doubts, please let me know. No doubts? Okay.